Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. So, Kalman filtering, second lecture. Inshallah, we're going to be continuing in the same discussion that we had about trying to solve the localization problem, which is again very tightly coupled to the sensor fusion problem. So, let's see. Today, inshallah, we're going to be doing as usual a recap. We're going to go back to the same examples we ended with last lecture, and then I'm going to tell you today about the Kalman filter algorithm. Okay, so this is really the most. It's not the most difficult part of the course. Maybe a couple of lectures more, but this is really the most important, algorithm that you should get out of the whole course, and it's much more powerful than you can imagine. And it's actually simple in terms of implementation, okay? And this is relative, okay? Depends on how you look at it. And then we're going to look at it, an application of it for the 1D robot estimation problem, the same example we ended with last lecture. And this is also part of what you should be doing in the assignment, okay? So this is tightly coupled to your current assignment. So let's start with the recap as usual. So this is the robot localization problem. We want to estimate where the robot is. We don't use just one position and one orientation. We represent it by a belief, by a probability distribution function. And this probability distribution function of the robot, of the state of the robot, so X here is the state of the robot, and it's given all of the Y information that we have. So the Y information is usually the sensory information that we have about the robot and also the previous state. So we said that we're going to be using Gaussians for that. So Gaussians will be the main probability distribution function that we're going to be using throughout. This is the whole idea of the Kalman filter. The Kalman filter just assumes everything is a Gaussian. Even though if the real robot is not a Gaussian, it just makes this assumption, and then you can, when you apply to the real robot and you can evaluate, you can actually see whether you need whether your robot really satisfies or your problem really satisfies this assumption or not. This is the multivariate Gaussian function. So it's a function of X. It's only determined by two parameters, the mean, which is a vector, and the covariance, which is a matrix. So this is a k by 1 vector. This is a k by k matrix. And the random variable itself that we're interested in is also a k by 1 vector. Okay, so X here is a vector, mu is a vector, while sigma is a matrix. And this was the toy problem that we had, and the toy animation, if you remember, of a 2D Gaussian, and we play around with it so that you can get an idea of how does the covariance change, the shape of the Gaussian, and also how does the mean change the Gaussian. And this was the framework we're going to be using to solve the robot localization problem. It's called the Bayesian filtering. It's based on Bayes' rule. You remember Bayes' rule was just this: you multiply the likelihood by the prior information, you get the posterior probability distribution function. The whole idea of the Bayesian filtering is that at any time step, so you start by time step k minus 1, right? And then you would and this is the belief of the robot, so this is our belief of how the robot, the probability distribution function of the robot in the previous time step, and we want to advance it to the next time step, okay? So we want to move from belief of k minus 1 to belief of xk. And this probability distribution function, we're going to be advancing it by one step, by the prediction update using the state transition model, and then we're going to be correcting that using the sensor model. And here, so this is the way how the Kalman filter is presented. And usually here you assume that you have a control input U, and this is the input to here is the measurement Z. But in practice, when we're doing the sensor fusion, both of these stages actually they have sensory information. So here this is usually the observation model, how the exteroceptive measurements affect the state, and here this is the proprioceptive sensor model. So how the proprioceptive sensors affect the state. So you see here this is a probability of xk given xk minus 1 and given the previous states. Given the previous state, the previous measurements, and also the latest proprioceptive sensor measurement. So here UK is an input here, and here ZK is an input. Okay. So this is usually how the Bayesian filtering works, and you just run this algorithm as fast as you can. So this is not yet an algorithm; it's just a framework. And then last lecture, we looked at the state transition model and the sensor model in details. So when we looked at the state transition model, so we said that what the Kalman filter will do is that it assumes that all of these three probability distribution functions, this one, and that one, they're all Gaussians. And it assumes that this state transition model is linear and this sensor model is linear. So everything is either linear or Gaussian. Okay? And the whole idea what this is very easy to work with from a probabilistic point of view is that when you have a Gaussian that goes into a linear model, the output is a Gaussian. Okay, so that's the whole idea. If you have a nonlinear equation and you give it a Gaussian, the output is not necessarily a Gaussian. So even if you start with a Gaussian and you enter a nonlinear equation, the output in general is not a Gaussian. However, if you have here a linear model and the input is a Gaussian, the output is usually a Gaussian. And then we looked at the state transition, this idea of linear state transition models. And we said that it's written by a difference equation like this. So usually you have that the next time step, xk, or the current time step, is equal to some matrix f multiplied by the previous vector, the previous state, xk minus 1, plus another matrix b multiplied by the u, how the proprioceptive sensor entered the equation, plus some noise. So vk here is some noise. And the z, the measurement model, which is the relation between the state and our observation, our exteroceptive sensor, is usually given by, it's related to the state by some matrix k, and also we have the noise wk. And this, because this is not just an equation that's deterministic, it's actually probabilistic. For example, vk here is Gaussian, xk minus 1 is a Gaussian, and we said uk is just, assume it's just an input, it's a constant. And thus we have that this is an output that's a Gaussian. So this is the idea, we have just addition and matrix multiplication. Addition and matrix multiplication, this is just linear operations. And thus, if the inputs are Gaussian, the output is a Gaussian. The same here. We have, we have a linear equation. We have, if this is a Gaussian, this is a Gaussian, this is a Gaussian. And then we said that we're going to be denoting the mean and covariance of this variable by xk hat and pk, and the mean and covariance of this variable by zk hat and rk. Okay? So in summary, so this is the whole idea, is that we assume that the state transition model is given by a Gaussian, and the measurement model, the likelihood, is given by another Gaussian. And then we said that the state transition model, okay, is simply, this is random, and this is known. xk minus 1 is random, vk is random, uk is known. And you get as an output random xk. And we said that if we know the Gaussian of this variable and the Gaussian of this variable, how can they be related to the Gaussian of this variable? And we said that it's given by this expression. And this expression, I said, you'll see it so many times. And it's very intuitive, okay? So, but when we go to the Kalman filter algorithm, we're going to have 4 or 5 of these expressions, but different variables, but it's exactly the same idea. So the whole idea of that is that if you have a linear model and the inputs are Gaussian, so for example, I want to know the mean of xk, so it would be equal to the mean of xk minus 1 multiplied by fk, the mean of the uk, but the uk is not a variable, so the mean of uk is actually uk, multiplied by bk, and the mean of this variable multiplied by just the identity, so just plus the mean. And we said that the noise here always has a 0 mean, okay, because you just have some noise there that's always in addition to the variable, so this is always 0 mean. So xk hat is equal to fk xk minus 1 hat plus bk uk. That makes sense? So this is exactly the same equation. We just took the mean of the variables. And now for the covariance of this, it's equal to something related to the covariance of this, xk minus 1. The uk does not have any covariance because it's not a random variable, so we just remove it. And we have the vk is another random variable that has a covariance. You see here, vk, the covariance of dk is qk, so we just add it as is. So we say that pk is equal to qk plus pk minus 1 is the covariance of this variable, and we pre and post multiply by fk in this way. Okay, so we just do it's called a similarity transformation. Sorry, it's called a congruence transformation. So fk transpose. Okay, so you see, you just give me xk hat, xk minus 1 hat, and uk, and the covariance of the noise and the previous covariance, and I can calculate for you pk and xk hat. Okay? So this is the whole idea of that. If we know what the Gaussians on the right-hand side, I can compute the Gaussian of the left-hand side. That's exactly how it looks like. So this is what we did for the state transition model. For the measurement model, we said that we're going to be introducing a new variable called the innovation. So the innovation here is the difference between what you measure with the exteroceptive sensor and how you think the model should behave. So your model of the sensor. Okay, so this is the idea where you do the sensor modeling, and this is exactly what we did in topic number 3, if you remember, when we modeled the IMU and the magnetometer and the gyroscope. And we're going to come back to that later when we discuss, how can we do a sensor fusion for the IMU. But for now, these are just general. So the measurement model simply takes a random xk, a random wk, which is the noise, and the known measurement that you get from the sensor, and you compute, you say, okay, this is the output, which is a random beta k. So this is the random innovation. And again, the same question, if we know what the Gaussian on the right-hand side is, can we compute the Gaussian of the left-hand side? And it's exactly the same expression. Exactly the same expression. You have here the same equation for the means and the same equation for the covariance. Okay. The only thing is that the covariance of the beta here, we call this, the mean is beta hat, and the covariance is called sk. And here you see we use the same equation, but with the means, and the mean of the wk is also 0, that's why it doesn't appear here. And the zk is a known variable, so that's why it doesn't have any covariance. And thus, it's the same equations. Make sense? Okay. So these two equations, actually it's just one equation, which is if you have a linear model, how do you relate this? How do you relate the right-hand side to the, how do you relate the input Gaussians to the output Gaussian? We're going to be using it again and again. You're going to be seeing it just, appearing many times today. Sorry? The mean and the covariance. So if I have a mean and a covariance, and I know the mean and the covariance of these variables, how can I compute the mean and the covariance of that variable? Okay. So the whole idea is that the z, the x, and the w, in this case the x and the w, they are Gaussians, and they enter the model, this is the model, and this is another Gaussian. So what is the mean and the variance, the mean and covariance of this Gaussian, if I know the mean and the covariance of these two Gaussians? So that's exactly the whole idea. This is exactly this equation. We're going to go back to the example. So these are the two toy problems that we're going to be playing with. The first one is this 1D estimation problem. This is the same as what you had in the assignment. Okay, and this is the level that you should expect in the exam and the quiz. The 2D robot problem is exactly the same as this one. It's just everything will be a little bit bigger. And this is when we start. By the way, you can do this on the paper. In the assignment you can do it by paper, but it just becomes tedious. And today I'm going to just derive how the state transition model and the measurement model of this example looks like, and this is what we did last time. I'll just remind you of how it looked like. So in this 1D robot problem, we said that we want to estimate the position of the robot, and the position of the robot is just psi along this line. Okay, so just assume we have a 1D robot. It's a toy problem. The control input here, we assume that we're measuring the velocity at 1 hertz. Okay, so every 1 second we just get a measurement for the velocity. And we observe the position every 1 divided by TS. So TS here could be is the sampling time for the position sensor. So assume, for example, we get every 2 seconds or every 5 seconds, the measurement for the position. And the whole idea is that we want to, and again, the two sensors, they are not perfect. So I don't get, exactly the real measurement. I don't get exactly the real position and the real velocity. I always have some, what? What is this eta and w here? Error. Not error. Noise. They're noise, exactly. So they're not a bias. Okay? The bias is another story. You remember when we discussed the IMU, we said we have noise, we have the stuff that we can move by calibration, for example, the biases and all of the misalignment stuff. We're taking the simplest problem, which is how to even handle the noise. The noise is inevitable. You cannot buy a sensor without noise. So W here is the noise that you have on the position sensor. Eta here is the noise that you have on the velocity sensor. And this symbol, what does this equation mean? I mentioned it last time and I repeat it again because this is very important. What does this, how do you read this notation? What does it mean that eta of t tilde n0 sigma u squared. What does this mean?
Can I guess? Because I wasn't there.
You weren't there?
Yeah,
Okay.
So, but I can guess.
Guess.
So n of t, which is the noise,
Eta of t is the noise, that's correct.
distributed normally with the mean 0 and
Has a comes from a normal distribution, that's correct. And if you say it's a normal, again, what's the normal distribution?
Gaussian.
The Gaussian. What does a Gaussian have? Only two things.
Yeah, the mean, which
A mean,
and the
which is 0, and in this case, it's just a variance. That's why we say it's sigma u squared. It's a variance. Why is this a variance, not a covariance?
but it has one.
It's a 1D problem. Okay, so sigma u squared here is just 1D. It's a one variable, and the covariance the covariance is always between two variables. And when we say the covariance of one variable with itself is just this is exactly the variance, okay, sigma u squared. So this is the variance of the sensor that you have that measures the velocity, and this is the variance for the sensor that you measure with the position.
The 0.
Sorry?
The 0.
The 0 is the mean. We always assume that the noise itself has 0 mean. We always call it's a white Gaussian. White Gaussian means that it's exactly when you say that my position is here, plus or minus 1 centimeter, or plus or minus 2 centimeter. You're thinking about, it's always something added to where you are. So it's called white Gaussian noise. You have a question, Mohammed?
Yes, it's a function of time, right?
Yes, which means it changes.
Yes, but maybe I'm mistaken here, but I remember a statistic when something is related to time, we use something, I think, exponential distribution.
No. So that's something else. So what I'm saying here is that the measurement at time t is equivalent to the position at time t plus a noise that depends on time. Okay? I'm not saying that the variance changes with time. Okay? I'm just saying that if you want to calculate if you want to calculate the noise at time t, you get it from a Gaussian distribution. That's what this says. Okay? And the kinematic model, okay, you see it's x dot is equal, the x here is the psi, so psi dot is equal to v. That's the simple model that we're using. Again, because of this simple problem. We're going to look at it, more complicated stuff. How do you go, the reason I put the bracket and the time here, I put it explicitly, is just to tell you that this is explicit, this is a continuous time. When we go to implement this as an algorithm, we need to discretize it. And that's the first thing that we did last time, is that we said, assume, so we have a discretization rule, which is given by just the simple backward Euler. We say that the velocity, or any variable here, so x here can be any variable, xk dot is approximated as x at time k minus x at k minus 1, so the previous time step, divided by the delta t, depending on how your sampling time in your computer or your microcontroller. So the x dot as a function of time, and this is equal to the psi dot as a function of time and v as a function of time, is equivalent to, just you can represent it last time, we did this on the board last time. We said that it's equivalent to this state transition model, that xk is equal to xk minus 1 plus delta t multiplied by uk plus the noise, and that the measurement model is equal to xk plus the noise. That's exactly what we did last time, and you see here, this is a very simple problem where the f and the h, so the matrix that relates xk minus 1 and xk is just 1. Actually, there's actually no matrix, it's just constant given by 1. And here there was a matrix that relates the xk to the zk, which we called it h, which is also 1. And then you have here the matrix that relates the uk to the state is given by delta t. Okay? And the noises, they have these variances. Okay? So everything is just, this is the simple problem, how it looks like. This is what you have in the assignment. And you see, if you're given what the eta w and the uk are at different time steps, you can just recursively use this equation and calculate xk given the previous time steps. You can calculate xk and the zk for different measurements. And that's exactly what you have in the assignment. So in the assignment, you have a table that you need to fill, and it's exactly just this equation. You just start from xk, you start from x0, and you start, just calculate x1, and then after you calculate x1, you calculate x2, and so on and so forth. It's very easy. Just so that you can practice, you can get a clear idea what's going on. Of course, when we do this, we do it with a computer, so you can do it as fast as possible, and you can, the x here can be very big, okay? And that's exactly, I'm gonna give you, this is still very small example, just calculate it to see how it looks like. Another example, but now we're gonna be estimating a 2D robot problem. It's a very simple problem, where but we don't want to estimate only the position of the robot, we also want to estimate the velocity of the robot. So here, our x is 4-dimensional. Okay, so I have psi1 and psi2, and v1 and v2. Okay, or psi1 is maybe position in the x direction, psi2 position in the y direction, and v1 is velocity in the y direction, x direction, and v2 is the velocity in the y direction. The control input, what I'm going to be using here in the state transition model, will be the acceleration. Okay, so I have here the acceleration. I'm using an accelerometer, and the accelerometer is related to the velocity, as you know. And I'm going to also be measuring the position of the robot. Okay? Again, at different time intervals. So here, every 1 second, I measure the acceleration, and every 1 over ts, every ts seconds, I'm measuring the position of the robot using this position sensor. And now, eta is, what's the dimension of eta? It's 2-dimensional, and w is 2-dimensional. Because you see, I have 2 states here and 2 states here. And this is the kinematic model. The kinematic model is also as simple as that the rate of change of the position is equal to velocity. The rate of change of the velocity is equal to the acceleration. Make sense? And now we can also use the same discretization law. Okay? But now I do it for both of these. Okay? Now let's do it on the board together. Okay? So this is, in the end, we should get this equation. Okay, but let's just take this equation and try to derive it ourselves. Okay, it's very easy, but I just want to follow the math, and later on, actually, this you can program it and you can do it in MATLAB very easily. Okay, so let's do it on the board, on the whiteboard, or blackboard. So we have that x dot is equal to the psi dot and the v dot. Okay. And then we said that psi dot is equal to v, which is, if I discretize it, then I have, at every time step, the rate of change of the position is equal to vk, and the rate of change of the velocity at every time step is equal to ak. You agree? And we said that our discretization rule is that this variable will be approximated by psi k minus 1 divided by delta t. So this is equal to vk. And this equation will be vk minus 1 divided by delta t is equal to ak. Make sense? Okay. Same equations. And now the first equation, I can rewrite it as psi k is equal to psi k minus 1 plus delta t vk. Okay. So vk is the state at the last time step. Vk, you see here, vk actually is which variable? Is which velocity? Previous time step or the current time step? The current one. Okay. And we said that we want the equation of motion to be something like this. We have xk is equal to something multiplied by xk minus 1, right? So this was the something here, we called it fk, this matrix. So we need always to relate the state at the previous time step to the next, to the current time step. Okay? And thus, this is not done yet. We need to still work it out. And actually, we can just use it from the other equation, that we have that vk is equal to we have that this is equal to vk minus 1 plus delta t multiplied by ak. The ak is not a state. This is actually the input. Okay? And this equation is not done yet because the vk is the current state, and we cannot use this equation here. So actually what we need to do is that we need to plug in this there. So this will be the first equation. Now if we plug 2 into 1, okay, so 2 in 1, what we get is that psi k is equal to psi k minus 1 plus delta t, but this delta t will be multiplied by vk minus 1, and then we're going to have delta t multiplied by ak, so we're going to have delta t squared multiplied by ak. Okay. Make sense? Okay. So now what I'm going to do is that I'm going to combining these two equations, so this equation 3 and equation 2, and then they're going to be looking like this. So if we take equation 2 and 3 together, this is what we get. I'm going to put them into a matrix, form. So I'm going to have psi k and then vk is equal to something multiplied by psi k minus 1 and vk minus 1. And then I'm going to have something multiplied by the input here, which was ak. Okay. And if you go back to the previous slide, you'll find that psi k is equal to 1 multiplied by psi k minus 1 and delta t multiplied by vk minus 1. So I have something that looks like 1 here and delta t here. And in the second equation, vk is equal to 1 multiplied by vk minus 1 and delta t multiplied by ak. So I have 1 multiplied by vk minus 1, and this was 0. And then I have here delta t multiplied by ak. Is this done or not yet? We still had another term here. So this was delta t squared. Okay. So if we go back here, you'll find the psi k is also related to the ak by delta t squared. Okay. So this is how the equation looks like. But this is still not the state transition model. It is the state transition model, but not the one that we're going to be using. Because if you go back to the slide, let me share. So if we go back to the slide, you'll see that what we actually need here is the u that you use for the sensor measurement. Okay? Not just the acceleration. We want actually the measurement that comes from the accelerometer or the velocity or the position sensor. So you see here, the a is the true velocity, is the true acceleration, sorry, and the u is the measured acceleration. The same also here for psi is the true position of the robot, while z is the measured position of the robot from the sensor. And that's why they're always related by this measurement noise. And thus, and actually what we need to do is that we simply plug in, these equations, and you can simply see that what we're going to get is that we're going to get the noise now. So instead of using the a, this will be actually the u, plus now we're going to have some noise, but we're just going to call this whole noise something like, let's call it eta k, as we said. Okay. So all of this stuff that's remaining here is just eta k. So this was the state transition model. And you see what's inside of this term. All of this matrix, this is simply f. And you see it does not depend on k at all. So it's just a constant matrix f. And this is another constant matrix b. So this is f multiplied by the previous state equal to the current state. So, and this is xk, and this is xk minus 1. Okay? So you see, the state at the current time step is equal to f multiplied by the state at the previous time step multiplied, plus a b multiplied by the input here. And this input is simply the acceleration measurement. Okay? And of course, this is just the noise. So this was the first equation. If you do exactly the same, but in the second equation, it's actually much easier. So in the measurement model, so this is the state transition model. State transition model. In the second equation, which is the measurement model, it's actually much easier because what we were measuring here, so the zk, is simply the psi k plus the noise that was there, so what we call w. Okay, that's it. Okay. So the hk in this example So the HK is simply the identity matrix in 2 dimensions. Okay. Make sense? So you see, we started with the simple kinematic model, the one that relates just velocity and acceleration and position and velocity, right? Simple, differential equation. And using this discretization, you can simply put it into this difference equation, and this difference equation will have the noise. And this is a linear equation, and this is another linear equation. And after you identify the whole idea of actually when you do this modeling is that you need to identify 3 things. You need to know what is the F, what is the B, what is the H. So this is of your model. And also what you do with that, what you also do in addition is that you need to know what is the covariance of the noise of eta and what is the covariance of the noise of the W. Okay? So the R. So these are the equations, the model that you have for your system. And these, they tell you what is the covariance of what we call the process noise, okay? And this is the covariance of the measurement noise. Okay? So this is usually called the process noise, and this is called the measurement noise. And again, I'll repeat the same remark because it's very important so that you don't get confused. Even though we call this as process noise, it's also related to a measurement that we get from a sensor. And even we call this a measurement noise, it's also related to the noise that we get from a sensor. Okay? Usually, this is the standard practice that we do in robotics is that in this step we use the proprioceptive sensors, and this step we use the measurement sensors. Okay? But in the reason why we don't call this a sensor and this is a sensor is just this is how people have thought about Kalman filters. So just to be consistent when you read any something, even when you use even ChatGPT, by the way, because ChatGPT just comes from all of the text that's out there. So when you're talking to ChatGPT, it will always tell you that this is called the control vector, the control input, and this is the observation input. This is Z is the observation, okay, and U is the control input. Even though they are both could be sensors, okay? They can be real sensor that you have on your robot. Okay, make sense? This is exactly the stuff that you need to know so that you can start using the Kalman filter. And that's the whole idea. We do the modeling so that we can get these and we use them for the Kalman filter algorithm. And that's exactly what we're going to be doing next. Okay? Any step before we move on? Any question? Yes?
What is the second equation?
Second equation, which is
I mean
the ZK.
First one gives the position and velocity.
It relates the position and the velocity, which are the state that you want to estimate with your Kalman with your equations. You want to estimate the position and the velocity, and you relate them to the previous position and velocity, and whatever input that you have, control input that you have, and this is the extra measurement that you have, the extra sensor that you are using. So you remember we said here we have 2 sensors, right? One which is the accelerometer. You see, this is the accelerometer.
Yes.
And this is, I forgot actually to put it here. So this is actually, so you see here, this variable is actually the position. I don't know why it's doing this. So this is the position measurement, the sensor. So you see, I'm measuring position, of course, and you say, okay, I'm measuring position, and of course I have, and with the state I want to, estimate is also the position. So of course it has to be, directly related to that. Okay. But there is something here that's a little bit, it's missing, and it's misleading. That the state, what the H was. So this actually was a typo here. I made something wrong. What you should be relating the position, the position measurement, you should relate it to the whole state, not just to the psi. Okay. So actually, this equation should be. Let me write it like this. Should be 1 multiplied by psi k plus. Let me remove all of this. Plus 0 multiplied by vk. Okay? Or in other words, I can rewrite it as 1 and 0, as a matrix, 1 and 0, multiplied by psi k, vk, plus the wk. Make sense?
So it's a loop, right?
This one? No, it's an equation.
So if I like to code, I love the first state,
Yes?
then it goes, the result goes to the new model.
The loop you're talking about will be through the prediction and then the update. This is what's used for the prediction step, and this is exactly what's used for the correction step. Yes, exactly. Yeah. But you see here, the point I want to make here is that the H, which is this matrix, HK, you see this is the H here, it relates the state at time step K to the measurement that you have, the observation that you have, that you're going to be using for the correction time step. So this is the measurement model you use for, used for the correction. And this is the state transition model you use for the prediction. And I'll tell you exactly what do we mean by the prediction and the correction when we go back to the Kalman filter in a bit. Okay? But at least, is it clear how you go from the kinematic model that we started with to this state transition model and the measurement model? Make sense? Okay? Typical example, example question that you also need to, to practice on is that I give you some, I give you some kinematic model, some differential equation. I tell you write it into this form. Okay, so that's exactly this exercise that we're doing. So now what we have. So I'll go back to the slide. So I'll give you now two examples. So this was this idea, okay, the state transition model, where we see how the previous states are related to the next states, and the measurement xk is related, the zk is related to the xk by the h. Okay, and these are the stuff that we just derived together. Make sense? Okay, and you see something again. Just a little bit different from what I said. I mentioned that the h is 1 and 0, but actually the psi itself was 2 by 2, and the psi itself was a 2 vector, and the v was a 2 vector. So here this is just a 2 by 4 matrix. Okay, if you go back to and check the dimensions, you see everything matches together. Okay, so this stuff when you're studying it, take your time to actually go through it bit by bit and to rederive it. Okay. Now the Kalman filter algorithm. Okay. So now we did. I think this is now our fifth lecture. So we started 13, 14, 15, 16, and this is our 17, lecture 17 on the same topic. And this is how it where it comes to. Okay. The Kalman filter algorithm. This is where you go to the computer and you just implement it. Okay. The Kalman filter algorithm. Okay. It does the following. It uses the state transition model, okay, to do a prediction step, and uses the sensor model, which is here written in terms of the innovation, beta, to do the correction. Okay? And these are two stages that you do to go from the Gaussian, okay, that corresponds to your robot belief, to your robot state at time step k minus 1, to go to step k. So the algorithm itself is something it's just a loop, and the only thing that you see is that you give it this and it gives you that. You give it this, you give you that. You give it this, you give it that, and so on and so forth. So the input and the output to the algorithm is just two things: the Gaussian, the mean of the Gaussian, and the covariance of the Gaussian. The mean and then it updates. It gives you, after you finish the whole loop, it gives you a new mean and a new covariance. That's it. And the mean and the covariance that you get at every time step are simply how you think, what the algorithm has the best idea about where the robot is, or the state of the robot in general. Okay? When I say the robot is, it's not necessarily that you're always estimating the position. In the previous example I showed you, for example, the 1D I want to estimate the position, while in the 2D I was actually trying to estimate the position and the velocity. Okay? Now note here the notation we're going to be using. Okay? The notation is a little bit heavy. Okay. If you look at it for the first time, but it actually will, after you get used to it, it becomes very easy, just to use. The belief at xk of xk minus 1, we're going to be representing it by this mean and this covariance. The mean of this Gaussian will be called x hat, but we're not going to be calling it x hat k minus 1. We're going to be calling it x hat k minus 1, and we're going to be putting this bar, and then we're going to be saying k minus 1. So x hat k minus 1 bar k minus 1. This is all of this symbol is the mean of this variable, and all of this symbol, which is p k minus 1 bar k minus 1, is the mean of that variable. Okay. Sorry, it's the covariance of this Gaussian. Sorry. And now, if I go after I finish the loop and I come to this part, which is the new Gaussian after I finish the Kalman filter algorithm, I get x hat k bar k and pk bar k. Okay, and I did something. Okay, does that make sense? So you see, the belief at xk is simply given by x hat k bar k and p k bar k. Okay, make sense? The reason why we introduced this bar notation is that just to differentiate between this mean and this covariance before the prediction and after the prediction. So before the prediction is given by these two symbols, and after the prediction they are given by these two symbols. Okay, and take a look at it so that you really see. Okay, just contrast them together. The mean of this Gaussian is x hat k minus 1 bar k minus 1, while the mean of this Gaussian is x hat k bar k minus 1. Okay, so you see here before the bar k, after the bar k minus 1. Here before the bar k minus 1, after the bar k minus 1, and here before the bar k and after the bar k. That's the whole idea. Okay, make sense? So these are three means that correspond to three different Gaussians. Okay? This is the Gaussian that corresponds to our robot belief, in the prior robot, prior belief about where the robot is. This is the Gaussian after one step update. We just updated, we haven't finished, by the way, the whole loop, right? This is just an intermediate step. After we do the prediction, how do we do the prediction? We do it with the state transition model. And then afterwards, you take what you just calculated here, the mean and the covariance, and you do a correction update to get a new mean and a new covariance that are called x hat k bar k, pk bar k. That's the whole algorithm. Okay. So to abstract it a little bit, so the prediction update, if you really want to abstract, just as an input-output, how you would write it in a code, right? You just have a function that has inputs and gives you outputs. The input here are x hat k minus 1, so the mean of the previous Gaussian, this mean, and the covariance. And you also need the UK, we need the proprioceptive measurements. And then you do the prediction update using the FK, BK, and QK. The FK and the BK are the matrices that appear in the state transition model, like the one that we just calculated in the two examples. And the QK is simply the covariance of this noise variable. So that's what you do for the prediction update, okay? As an input and output. For the correction update, I take what I calculated here. I take the mean and the covariance, the last two I calculated here, which is after the update. And then I use extra stuff. I use also the ZK, which is the exteroceptive measurement. And I use here the HK, which is this measurement, what appears in the measurement model. And I use the RK, which is the covariance of this noise variable. Using all of these 5 pieces of information, I'll be able to calculate the mean of this Gaussian and the covariance of this Gaussian. This is the whole Kalman filter algorithm. Okay? That's the story of the Kalman filter algorithm. How it looks like now, it will be a little bit scary for the first time. You need to really spend a lot of time. Okay? But if you actually dissect it, it's very easy to understand, okay, given what we discussed so far. Any questions on this part alone, just from the input-output point of view? So what you have at the assignment, you have a Kalman update and a Kalman correct, two functions. These are the inputs and outputs, okay? And these are the inputs and outputs for the Kalman update. This is for the Kalman predict. Okay? So there are two functions, and you need to play around with them. You need to fill in them in. Okay, that's what you have in the assignment. And then you have a third file that actually implements the whole algorithm for you, and it does it with a GUI. And I'm gonna show you a little bit what you should expect from the result today. Okay, this is just the full picture of the Kalman filter. What is the algorithm now? This is the algorithm. Okay, which is scary, but this is one of the things that you print and you keep it in front of you when you're working with it. Okay, I advise you all to don't keep it on your slides, okay, on your tablets or computers. It's really best if you print it, to actually look at it every day before you sleep. Okay. So what you see here is the following. The whole algorithm, as I mentioned, just takes the state estimate, which is the mean, and the covariance of the Gaussian at time k minus 1, and we will propagate them to the state estimate at time k and the state covariance at time k. So the whole algorithm is that you start from here, you end up here. So that's the big picture. The first step that you do is that you do a prediction. So these are the two predictions. So this is the state prediction. You see, I use the state and the control, and I do an update for the state. And then I use the covariance. And you see here, I have the F and the Q. I use them to update the covariance. So I update the state. Sorry, I do a prediction for the state, and I do a prediction for the covariance. And then afterwards, I take the X hat and the P that I just calculated, and I compute the innovation. And to compute the innovation here, I subtract this with the observation, what I get from the sensor. So you see here at this step, I use the control input, which are the proprioceptive sensors. And at this step, I use the observation, which is the exteroceptive sensors. So I use these two to compute the innovation. And then afterwards, I compute here the innovation covariance. Okay? So this is the covariance that corresponds to this mean. So beta and S here are the mean and covariance of one Gaussian. X hat and P are the mean and covariance of another Gaussian. And then afterwards, we calculate something called the Kalman gain. And this is the key symbol or key parameter, sorry, the key variable that actually links the whole thing together. Of course, its derivation is way beyond this course. Okay. Last semester actually, so last time I gave the course, actually I went to the details and they took it very well, but okay, I did not want to put you into that suffering. Okay, so if you want, I can show you the details if you really want to know how to derive it. Okay, but if you want just from an implementation point of view, this is just a matrix called the Kalman gain. And you see, it's simply the multiplication of three matrices. It's the multiplication of pk, So this Kalman gain is the multiplication of three matrices. This pk bar k minus 1, which is what we calculated here. So this one. And it's multiplied by the h transpose. And the h here is what we got from the measurement model. And the sk inverse, sk here is the covariance of the innovation variable. Okay? So the sk inverse. After you calculate the Kalman gain, you use it to correct for the state and to correct for the state covariance. And afterwards, you just have them as an output. And you're done. All of this is what you do in one loop. Okay? Of course, if you're running the Kalman filter as, let's say, 1,000 hertz, then you run this, this whole loop in 1 millisecond, and so on and so forth. Okay, just keep on doing. Your phones, they have something like this implemented, a little bit more advanced. If you have a PX4, for example, or Arduino Pilot, it's implementing something much more complicated than this. It's similar to this, but it's also but much bigger actually. Okay, so for example, the one that you have, and we're gonna come back to that in a future lecture. the state that you have in, for example, in the PixHawk is actually a 24 state. So you just have a 24. And now imagine that all of these matrices are just 24 by 24, and you should run all of this, in 1 millisecond, of course. Of course, the hardest, from a computational point of view, so that's a like intelligence question. Let's see how smart you are with using computers. Which do you think the hardest part computationally is actually in all of this? So what is the thing that would actually take the most time if you're computing this? And by the way, you can try it at home. So when you have your MATLAB code, it's not implemented, but you can dig in and actually compute how much time that you take for all of these steps, and try to identify what is the bottleneck. So it's usually called the bottleneck or computational bottleneck. It's the part that takes the most time during the computation. Which one do you think, just from looking at the equations? Try to guess. So which block of all of these steps takes the most time on the computer?
I think the lower one.
Which one? It's only one block out of all of these.
Could be the Kalman game.
Why? So the answer is correct. It is the Kalman game that's the most complicated, but why?
3 matrices.
That's not an issue.
But could be long.
It's true. The Kalman game is the most computationally intensive part, but it's not because it's multiplication of 3 matrices. That's easy to do. The hardest part is what?
Is this something happened before?
No, it's inside of this block. Yes, exactly. It's the matrix inversion. The S here has a dimension the same as the innovation, okay? So let's say that the innovation here, for example, was 10 vector. So the beta here is 10 vector. Then the S here will be a 10 by 10 matrix. Computationally, doing the inverse of a 10 by 10 matrix, usually can be, hard. Of course, as we go even further, the inverse usually gets, it increases with a computational of n cubed. So if I go from 10 to like 20, from 10 to 20, I shall multiply by 2. The computational computing the inverse of the 20 by 20 matrix will be 8 times slower, exactly. So it's even though I just multiplied by 2, so something like this, okay, and so on. You can imagine how so it's a computational complexity of n cubed, okay. So this is the bottleneck, okay. However, with recent advancements and how computers are getting faster every day, and all of this idea of parallel computing, usually there are better ways of implementing this, but the same idea holds. So to conclude, this is the Kalman filter algorithm, okay? So just in a bottom, in a nutshell, you start by a Gaussian. You do using a state transition model, which involves knowing the UK, knowing the FK, and knowing the QK and the BK, okay? And then I calculate from it a new mean and new covariance, these two. And afterwards, I take these two along with the measurement, the exciroceptive measurement, the ZK, and then I use the sensor model. So the sensor model includes the HK, and I just update with it the state and the state mean and the state covariance. So you see here, the Kalman filter in the end is an algorithm. Is just 1, 2, 3, 4, 5, 6, 7 lines. Okay, they're just 7 lines that you have. These 2 lines, they are the prediction step, and these 5 lines are the correction step. Okay, so inside of a code it's very easy. Of course, it involves matrix multiplication. Yeah? So that's the whole idea of why we wrote them in matrices, so that they are very compact. So they require that you actually have a way of handling matrices on your computer. Okay, of course, if you're using MATLAB, this is trivial. But if you're implementing this on a microcontroller, you need actually to use a library that allows you to write things with matrices and so on. And now let's look at an example. So let's see how much time do we have. Okay, so in the remaining time, let's look at this implemented in the lecture. Okay, after you implement the algorithm, let's play around with it and let's see what happens. Okay, this is what you had in the assignment. Okay, so you're given this. Okay, this GUI at home. Okay, and when you run your MATLAB code, it will not run. Okay? It will give you an error. Okay? And the reason why is that it's not complete. The code is not complete yet. Okay? So what you should do is that first you should complete it. Okay? You just follow the assignment, and then you should be able to run something like this. And then afterwards you use it to do some experiments. So you just play around with some stuff and change some variables there inside of the code, and then you document it in the assignment. Okay? This assignment takes a lot of time, and I already mentioned that in the announcement. Okay, so you really need to start. When was the deadline for the assignment? Thursday? Yeah. Okay. So, but you better work on it quick. Okay. Don't leave it to the last minute because it really takes a lot of time.
No,
okay?
Tuesday.
Tuesday. Okay. Before the lecture, right?
Not sure.
Okay. I think it's Tuesday before the lecture. So if you haven't started try to do it today. Let me show you now the code. For the lecture, yeah. And there's a reason, okay, so that, before you really need to understand, what we're going to be discussing, because next lecture things will be a little bit, the level will go high, so you really need to devote some time studying this. Do you have any majors this week?
Yeah.
When?
Thursday.
Okay, good. Okay, so still time. So do it on Tuesday, then you have Tuesday evening and Wednesday to study for the major. What? If we do that, then next lecture will be as like this, desert, okay, intellectually, okay. So I really need you to finish the assignments because next lecture will be depending on this, and even the one afterward depends on both. So So this is after you. Yes, I'm done.
الأسايمنت هذا الكودينج بيجي في الفاينل يعني والله.
So how maybe let's leave that question later on. How it will appear in the final, okay? So the final will be a mix of coding and some theoretical stuff. For now, focus on the assignments, okay? Okay, and I just finishing them, and later on I'll tell you how to prepare for the final, okay? So this is what you should get after you run the code, okay? So after you fill it in, and you should be getting this. The filling in part is very easy. It's actually, if you really want to do just from the lectures, it's trivial. ChatGPT will do it, even trivially, okay? So that's not the issue. It's actually just 2 lines or something, that are really missing, or 3 or 4 lines maximum, I think. But afterwards, after you run this, you need to actually play around with the GUI. So, and I think ChatGPT will not be able to do that for you. So you have to do it yourself, okay? What you see here is the following. On the top is our 1D robot estimation problem, okay? So this is where the robot is in real life. So this is the true robot. And this is, what is this, Gaussian, do you think? This is our belief about the robot state, about where the robot is. So this is where the robot truly is, and this is where the robot believes it is. Okay? And as we said, it's not just one point, it's actually a Gaussian distribution. So the robot most likely thinks it's in this location, plus or minus, right? You have this Gaussian. Okay, so this is the plus or minus, okay? Intuition. And then on the top here, you find this is just the history. So this is just position as a function of time, okay? So as we move along, you'll just see this, position go up and down. Where do you want to start? Okay, let's start. You can choose the robot. You can put it. Start from here, and now you can actually start to drive it. The way you drive it is from the keyboard. Okay, so if you just move to the right, I move 2 steps. Let's see.
But he's not.
Yeah, I think there's just a bug here. So 1 second. Let me clear this. Yeah. Okay. I think I know. I think I use this. Yeah, okay, so that's correct. Okay, so also this is also another bug. I'll tell you about it. So once you choose the position here in the code, Okay, from this slider, the focus of the keyboard is actually on the slider. Okay, before you move with the keyboard, just press anywhere here, with the mouse, okay? So that the focus is away from the slider. So that was the reason. Okay, so I'll start from this point, and the initial state will be, let's say, here. Remember, what is this initial state? Which variable is this initial state here? What was it? What is the initial state and the initial variance that we're talking about here? The initial state was the mean of this Gaussian. So it was the x hat at time step 0. And the initial variance is the p, the covariance of the robot, of the state, at time 0. So this is x hat 0 and p 0. What we use for the initialization. You remember this is a recursive algorithm, so you cannot start with some initial condition. So this you cannot start without an initial condition. So these are the initial conditions that you start with. Okay. So I'll start. So what we're going to be doing here is that we're going to be telling the robot, you are here. Okay. So let's start. Let's actually do it a little bit different. Let's tell the robot you are here. Okay.
So we can be off, and he will.
We'll see. We'll see. So this is where we tell the robot where it is. Let me move it a little bit. Okay, so this is where I think the robot is, and this is where the robot truly is. You all agree? And now what you're going to be doing is that you just drive the robot. So we're going to just teleoperate it from the keyboard. So just move right, okay, and left. So you see what happened? Did anyone capture what happened first?
It was displaced. Like he got corrected.
Got corrected by what? By this green dot. You see this green circle here? What is this green circle here? The measurement that you get from the sensor. Okay? So I have a measurement. Okay? So this measurement is the Z. And the U is used from the keyboard. So actually, when I'm moving it with the keyboard, this is actually the U. I'm just moving it around. Okay. So again, let's continue moving. So did you get what's going on here? I'll do it again. So I'll press 8 times, and take a look at this curve. Okay, what's going on with it? So it starts by this, and then I'm pressing 1, 2, 3, 4, 5, 6, 7, 8. So tell me, what did you observe?
So he was.
So someone than Muhammad, different. So who else? Ryan.
After 8 steps, is more sure about the location.
After 8 steps, the robot is more sure about where it is. That's correct. What was happening when I was pressing during the 8 times? Again, let's repeat it. 1, 2, 3, 4, 5, 6, 7. What happened? Someone else غير Ryan.
It's not measuring what it is. It's estimating.
It's estimating, so it's getting less accurate with time. So what you're seeing here is that, so the way the way the code is implemented is that it gives you a measurement for the position every 8 seconds. Okay? So every second I press. So this is not implemented, by the way, in terms of time. Just so that you know, it's just implemented by time steps. And every time I press, we just advance in time. By 1 time step. Okay. So every 8 time steps, we get 1 measurement. Okay. During that, until I get the next measurement, what are we doing? We're just predicting alone. So what actually the Kalman filter is doing here, and this is something I did not tell you, but you can infer it from this demo, is that the prediction step of the Kalman filter is not necessarily to be done at the same time with the correction. What you're seeing here is actually the Kalman filter is running as the following. It's done prediction and no correction. Prediction, no correction. Prediction and no correction. So it's doing prediction 8 times. So it's doing 7 times. And the 8th is doing what? Is doing a correction. Okay? So this is how the Kalman filter is actually being implemented now. So I'm doing 8 times the prediction. What am I using for the prediction? I'm using the proprioceptive sensor, but not only that. I'm using also something else. What is it? I'm using the state transition model, not just the proprioceptive sensor. It's not enough that you just measure with the sensor. You also have a model about how the robot is moving. And the model here is very simple in this problem. It's just saying that the rate of change of position is equal to velocity. So if I'm having the velocity inputs, the one I'm pressing here by the keyboard, I can estimate where the robot is. But this velocity inputs are not accurate. They are noisy. So when I press 8 times, the more I press, the more I keep on predicting, what happens? I accumulate error. And this reflects into accumulating uncertainty. So when I press now, okay, we're going to get a measurement, and we're going to get very sure the uncertainty at one step just decreases a lot. The Gaussian, becomes very narrow, which means that, what does this mean?
Sure.
The robot is sure about where it is. Okay? The algorithm is sure about where it is. Okay? Yes, Mohammed.
So every 7 steps,
Every 7 steps, yeah.
we accumulate error, which is uncertainty.
That's right.
Does that affect every time we go to the 8 steps where he got corrected?
Yeah.
So for example, does it make it a little bit bigger? Because it's accumulated, then he drives the other.
That's an excellent question. Yeah. The way that you see here, so repeat it again. So let's play around with it again. I'll go back and forth now. So imagine what's happening. Go back. Do you see this changing every time or not?
I'm not sure.
The way it looks like, it's most likely not. Okay?
Yeah, but like after,
So many times.
yeah,
That's exactly what you can do with this assignment. So take it at home. You have it at home. Play around with it and see exactly whether this, will be correct or not. Okay? Now I'll do something, even better. I'll do what's known as the robot kidnapping problem. Let's say for some reason, something wrong happens to the robot. At some instant, even though it's here, something happens and then it gets kidnapped and it goes there. Okay, actually I just reinitiated the whole thing now. Let's see. Okay, okay. So now the robot is here and it thinks it's there. And there is no measurement yet. Okay, so it just jumped a lot. And now I keep on moving. Let me clear the history. So now I keep on moving. So the robot is, let me press here. So the robot is moving, but now we got the measurement. I'll kidnap the robot again. So I'll put it here. And I'll keep on moving. So we should not expect the measurement except after 7 times. Sorry? Yeah, yeah, thank you. And now I'm going to be moving 1, 2, 3, 4, 5, 6, 7. You see what's going on here? You see the true robot's location and the measured, and the estimated one are too far away because of this idea. There's something wrong that happened and they diverted a lot. Okay, but after we get the measurement, what happens? Okay. It gets immediately corrected. Okay. And then after I move again, you just keep on working like this. So you see exactly what the Kalman filter is doing. It's fusing 2 pieces of information. It's fusing, first of all, the green dots, which is the exteroceptive measurements that we're getting, and we're getting them slow. We're not getting them very fast. We're getting them every 8 seconds. And it's also fusing with them the keyboard, which is our velocity sensor that we're using here in this example. So this is our velocity sensor. How I know how the robot, I'm telling it to move. Okay, so this is what I'm using, 2 pieces of information. Not only that, this is not enough. You cannot just get the two sensors and, we're not doing some averaging or, some signal processing in any way. We're actually doing estimation, which means that I need to have a model about how the robot will behave. And that's why we're using the kinematic model. And the Kalman filter is simply just, runs all of this loop again and again and again. And you just keep on, driving the robot and things will happen that you need, this is exactly what you're going to be experiencing at home. The way this behavior depends on actually the parameters I put in the code. Okay, so there are two parameters we need to play around with, which is the variance of the process noise, or in general, the covariance of the process noise and the covariance of the measurement noise. Okay, so these are the Q and the R, which are here, they are fixed. At home, you're going to be playing around with them, changing in the code, and then going here and playing around with it again, just driving the robot around and seeing how does this affect the performance of the Kalman filter. Yes, Mohammed? Time? Okay. So I'll stop here, okay? It's extremely important that you do the assignment before next lecture, okay? Because we're going to be continuing exactly on this example, and we're going to be, going harder and harder. Okay, next lecture will be hard. Okay, if you don't study and if you don't do the assignment, if you do the assignment, it will be still hard but less hard. Okay, so it will be reasonable, inshallah. Jazakum Allah khair. Let me stop the recording.